So before we get to this third equation of figuring out what happens to our differential equation when we have two complex solutions, we have to talk about complex exponentials. So we have to talk about complex exponentials. And a complex number is a number of the form a plus ib, where a and b are real numbers. So that's a complex number. So let's write this out. So the set of complex numbers is the numbers of the form a plus ib, where a and b belong to the real numbers. So this symbol, by the way, just means is an element of. A and b are elements of the real numbers. Elements just mean that they belong to the set. Okay, and so that's the complex values. And so what I want to do is I want to think about if you were to take some complex number z, you can write it as, so the generic way to do that is to write that as x plus iy. I want to know what is e to the x plus iy. The e to the x part is straightforward. There's no problem there. And you could think of this as e to the x, e to the iy. But what does it mean to take the complex number, to take the exponential of an imaginary number, e to the iy? Well, this is the thing that I want to focus on, this e to the iy. And it turns out that there's a really nice thing that happens here. And it's so nice that it's named after someone. It's called Euler's identity. And before I spoil it and tell you what Euler's identity is, let's think about what this is in terms of the power series for e to the x. So if you were to take e to the x as a power series, this is 1 plus x squared over 2 factorial. This is really x to the 1 over 1 factorial if you want to write that. I don't. Plus x cubed over 3 factorial, x to the 4th over 4 factorial, and so on. I'm going to go up to, say, 7. So x to the 6 over 6 factorial, x to the 7 over 7 factorial. Okay, so that's e to the x. Now let's think about what's e to the iy. If I were to take all the x's and replace them with iy, remember that I squared, I should have said this a long time ago, but I squared has the magic property so that when you square it, you get -1. And it turns out that if you were to look at e to the iy in a power series form, this is going to be 1 plus iy squared over 2 factorial plus iy cubed over 3 factorial, and so on. So iy to the 4th over 4 factorial, iy to the 5th. I need to slow down. iy to the 6th, iy to the 7th. Just squeeze that in there. Okay, and so that's if you replace all the x's with iy. And then I want to think about what happens when you take powers of I. Well, the first two terms, there's no powers really. We just have 1 and iy, so nothing there. For the second term, if we square I, we get -1. So this will be minus y squared over 2 factorial. For the third power, we're going to get I cubed. And I cubed is I squared times I. I squared is -1, so this is minus I y cubed over 3 factorial. And then I to the 4th is going to be I squared squared. So I squared is -1, -1 squared is 1. So you end up with 1 y to the 4th. And then this just repeats. Every fourth power is the same. So so I to the 4th is 1, just like I to the 0. I to the 5th is the same as I to the 1st. So that's just plus I. -1 minus I, and so on. And then what I'm going to do is I'm going to group the terms that have an I in them and the terms that don't together. And I'm going to write this as a sum of 2 series. So this is 1 minus y squared over 2 factorial plus y to the 4th over 4 factorial minus y to the 6th over 6 factorial, and so on, plus I times, let's see what happens when we factor an I out of the other terms. We're left with y minus y cubed over 3 factorial plus y to the 5th over 5 factorial minus y to the 7th over 7 factorial, and so on. And this first power series you should recognize is cosine of y. The second power series you should recognize as sine of y. You end up with e to the iy being cosine of y plus I sine of y. And this is called Euler's identity. So Euler's identity states that if you were to have e to the I theta, that's cosine of theta plus I sine of theta. Okay, and so that's Euler's identity. Euler was a mathematician. He's actually the namesake of the number e. That's how important he is. Okay, is that the number e is actually named after Euler. So it's an E for Euler. It's not Euler, it's Euler, like the hockey team or the football team. So that's Euler's identity. This leads to a very concrete connection, if you think about it, between geometry, trigonometry, and complex numbers. So this is a really, really, really crucial and very deep identity that connects these two seemingly disparate fields of trigonometry and complex numbers. If you were to think about e to the I pi, this is one example that people get very excited about, but e to the I pi would just be cosine of pi plus I sine of pi. And cosine of pi is -1, sine of pi is 0. So this tells you that e to the I pi is -1, which is pretty in and of itself. People get very excited, I think a little too excited, but people get very excited about this equation, e to the I pi plus 1 equals 0, because it's an equation that really ties together the 5 most fundamental numbers in all of math. So you have Euler's number, which is very crucial for calculus, I, which is crucial for complex analysis, pi, which is crucial for geometry, and then of course 1 and 0, which are important in and of themselves. So 1 being the multiplicative identity and 0 being the additive identity in the reals. So this is Euler's identity. What we'll do in the next video is see what does Euler's identity have to tell us about differential equations.